Welcome back, traveler. Tonight we explore something so familiar that it usually goes unnoticed. You look up at the sky and everything seems calm, fixed, almost frozen in place. The stars appear steady. The planets trace predictable paths. Even Earth, beneath your feet, feels solid and still, like a platform rather than a participant in motion. At first, spinning feels like a small detail. A planet rotates, a wheel turns. A galaxy slowly twists. It sounds like a cosmetic feature of the universe, not a fundamental one. You might even assume rotation is optional, something objects do only if they're pushed hard enough or nudged the right way at the start. But here's what most people don't realize. Spin is not the exception, it's the rule. From the smallest particles to entire galaxies, everything that exists seems to carry some form of rotation, twist, or angular momentum. And once you notice that pattern, it stops feeling accidental. It starts feeling structural. If everything spins, then time behaves differently than you expect. Space doesn't settle into perfect stillness. Motion never truly disappears. Even when systems collapse, merge and/or cool down, something keeps turning. And if rotation is everywhere, then the question isn't why some things spin, it's why anything ever spins at all. By the end of this journey, you'll understand where cosmic rotation comes from, why it refuses to vanish, and how a quiet rule written into the fabric of physics turns simple motion into a universe-wide inheritance. If you enjoy these late-night explorations, you can like the video, subscribe, and leave a quick comment telling where you're watching from and what time it is. Now, let's begin. The simplest picture most people carry is this. The universe begins, matter forms, and only later does motion appear. Something pushes, something collides, something starts to spin. Rotation, in this view, is a consequence, a secondary effect layered on top of an otherwise quiet cosmos. That intuition feels reasonable because it mirrors everyday experience. A ball on the floor does not spin unless you kick it. A wheel does not rotate unless you apply force. Stillness feels like the default state, and motion feels borrowed. But this is exactly where the intuition breaks. Because in physics, rest is not privileged. Motion is not something that needs permission. And rotation, in particular, does not behave like ordinary movement through space. It follows a different rule, one that turns out to be stubborn, conservative, and nearly impossible to erase. To see why, it helps to step away from the universe for a moment and return to something smaller and more familiar. Imagine a person standing on a smooth, frictionless surface, holding a spinning bicycle wheel. If they flip the wheel, their body rotates in response. No motors, no pushing against the ground, just rotation rearranging itself to stay balanced. This is angular momentum at work, and it behaves nothing like intuition suggests. Linear motion can be cancelled. Two objects moving toward each other at equal speeds can collide and stop. Their motion disappears into heat, sound, deformation. Rotation does not vanish so easily. When systems interact, angular momentum does not disappear, it redistributes. That distinction changes everything. If a system has even the tiniest amount of rotation, that rotation tends to survive every transformation that follows. Collapse concentrates it, mergers amplify it, cooling does not remove it. Friction may slow surfaces, but the underlying rotational budget remains. Now scale that idea up. Long before stars existed, before planets formed, before galaxies took shape, matter in the early universe was already moving, not in neat orbits, not in elegant spirals, but in turbulent, uneven flows shaped by gravity, pulling from every direction at once. Those flows were not perfectly symmetrical. They never could be. Tiny imbalances, quantum-scale fluctuations stretched by cosmic expansion, ensured that no region of matter fell inward in a perfectly straight, perfectly canceling way. And here's where the trap snaps shut. Once collapse begins with even a trace of asymmetry, rotation becomes unavoidable. Matter falling inward does not crash straight to the center. It curves, it deflects, it starts to swirl. And as the collapsing region shrinks, that swirl speeds up. Not because anything is added, but because nothing can take it away. At first, that sounds impossible, until you notice how familiar it actually is. An ice skater pulling in their arms spins faster without adding energy. A collapsing cloud of gas does the same thing on a cosmic scale. Radius decreases, rotation increases, conservation does the rest. This is why disks appear everywhere in the universe. Planets form from spinning disks of dust. Stars form from spinning disks of gas. Galaxies arrange themselves into rotating structures, spanning hundreds of thousands of light years. The shapes differ. The scales explode outward. But the pattern repeats with unsettling consistency. And once you see that pattern, it becomes difficult to imagine a universe without it. A universe without spin would require something extra. Such a universe would be exquisitely fragile. One disturbance and one quantum fluctuation, and rotation would reappear instantly. So the better question emerges naturally. If everything spins because angular momentum is conserved, where did the first angular momentum come from? That sounds like progress, but it opens a deeper puzzle. Conservation laws do not create quantities. They only preserve them. They explain why something persists, not why it exists at all. So if rotation is everywhere now, it must have been present then, at the very beginning, embedded into the universe itself. And that realization shifts the story once again, because now we are no longer talking about spinning objects. We are talking about whether the universe ever had the option not to spin. That question pulls us past planets, past stars, past galaxies, and straight toward the earliest moments we can meaningfully describe, where space itself was still deciding what rules it would follow. And that's where the story gets strange. To understand why everything in the universe spins, you have to abandon the idea of a clean beginning. No smooth start. No perfectly balanced fall. The early universe was not a calm stage waiting for actors to arrive. It was restless from the first moments we can meaningfully describe, filled with matter that was already uneven, already imperfect, already slightly out of balance, in ways that would later define everything. This matters because gravity does not act gently. It does not negotiate. It pulls relentlessly, and when it pulls on something that is even slightly uneven, the result is not a straight collapse, but a curve, a deflection, a turn that compounds on itself as time goes on. Imagine a vast cloud of matter stretching across space. Not yet a star, not yet a galaxy, just a diffuse collection of particles responding to gravity. If every particle fell inward along perfectly straight lines, their motions could cancel. But perfection is not an option the universe ever had. One region is always slightly denser. One direction always pulls a little harder. One particle always arrives a fraction of a moment earlier than another. Those tiny differences matter more than intuition allows. As gravity pulls matter inward, those asymmetries cause sideways motion. Sideways motion becomes circulation. Circulation becomes rotation. And because angular momentum cannot disappear, that rotation becomes permanent, locked into the system like a signature. At first, the rotation is weak, almost unnoticeable, but collapse changes the scale. As matter falls inward, the same amount of angular momentum is now packed into a smaller and smaller region. The rotation speeds up, not because anything new is added, but because conservation demands it. This is why collapse never produces spheres alone. It produces disks. The same process repeats across scales so different they are difficult to compare. A collapsing cloud that will become a star flattens into a rotating disk of gas and dust. Inside that disk, smaller clumps form, inheriting the same rotational bias. Those clumps flatten again, forming disks within disks, eventually giving rise to planets, moons, and rings, all spinning in roughly the same direction. Zoom out, and the pattern does not change. Galaxies form when enormous regions of matter collapse under gravity. They flatten, they rotate. They spin faster toward their centers, slower at the edges, but always turning, always carrying forward the rotational memory of their formation. This repetition is not coincidence, it is inheritance. Every structure you see is a descendant of earlier motion. Spin is passed down, diluted, concentrated, redistributed, but never erased. Even violent events like collisions and mergers do not remove it, they merely reshuffle it. When two galaxies collide, their stars rarely crash into each other directly. Instead, their gravitational fields interpenetrate, twisting trajectories, stretching arms, and producing even more complex patterns of rotation. The final galaxy that emerges from such a merger often spins faster than either of its parents, its angular momentum now redistributed into a new configuration. This stubborn persistence is what makes rotation feel less like a feature and more like a law. But there is still a deeper layer to confront, because everything described so far assumes that angular momentum already existed in those early clouds. Conservation explains why it survives, not where it came from. So the question sharpens, was the early universe already rotating, even before structures formed? This is where speculation must be handled carefully, because the universe does not give up its secrets easily. Large-scale rotation of the universe as a whole has been searched for, measured, constrained. If the cosmos were spinning globally, we would expect to see signatures in the background radiation that fills space, subtle anisotropies that betray a preferred direction. So far, observations suggest that on the largest scales, the universe is remarkably uniform. No obvious global spin axis, no cosmic whirlpool dragging everything around a center. But uniformity does not mean stillness. Even without a global rotation, local angular momentum can emerge naturally from the expansion and cooling of the universe itself. The early universe was not static. It was expanding, stretching tiny fluctuations into vast structures. As regions decoupled from the overall expansion and began to collapse under their own gravity, those fluctuations became seeds for motion. In other words, rotation does not require the universe itself to spin like a wheel. It only requires that collapse happens in a universe that was never perfectly smooth, and smoothness, again, was never on the table. Quantum mechanics ensures that uncertainty is baked into reality at the smallest scales. Inflation magnifies those uncertainties to cosmic proportions. Gravity then amplifies them further, turning microscopic differences into macroscopic motion. Spin is not added later, it is revealed. This reframes rotation as something almost inevitable. Given gravity, given expansion, given imperfection, spinning structures are not just likely, they are unavoidable. A universe with matter and gravity, but without rotation, would be more surprising than one filled with it. And once that perspective settles in, the ubiquity of spin stops feeling mysterious. It feels necessary. The real mystery shifts elsewhere. If rotation is unavoidable, why does it take the forms it does? Why do spins align within systems, but misalign between them? Why do some objects spin rapidly while others turn lazily? Why does angular momentum sometimes appear concentrated in unexpected places, like thin rings or jets blasting outward from compact objects? Those questions pull the story forward, because rotation is not just a relic of the past. It is an active force shaping how matter organizes, how energy flows, and how structures survive over cosmic time. Spin stabilizes disks, it powers jets, it resists collapse, it determines whether matter spreads out or falls inward. In many cases, it decides whether a system lives quietly for billions of years or tears itself apart. And that brings us to the next layer of the story. Because once rotation exists everywhere, the universe has to deal with it. It has to channel it, regulate it, and sometimes fight against it. That struggle between gravity trying to collapse everything and rotation trying to fling it apart is what sculpts much of the visible universe, and it is far from over. Once rotation is present, the universe can never ignore it. Gravity may initiate collapse, but spin immediately pushes back. What follows is not a simple victory for one side or the other, but a long negotiation, a dynamic balance that determines the shape, lifespan, and fate of almost every structure you can see. Gravity pulls matter inward indiscriminately. Rotation resists that pull by spreading motion sideways. The faster something spins, the harder it becomes for gravity to force everything straight down to the center. This is why collapse rarely ends in a single point. Instead, it stalls, flattens, and reorganizes. You can see this tension clearly in something as familiar as a star-forming region. A cloud of gas begins to collapse under its own weight, heating up as it shrinks. If gravity acted alone, the cloud would plunge inward until it ignited and consumed itself rapidly. But rotation intervenes. As the cloud contracts, it spins faster, creating a centrifugal barrier that prevents matter from falling directly into the center. The result is a disk. Material spirals inward gradually, losing angular momentum through friction, turbulence, and magnetic effects. That slow inward drift feeds the growing star while preserving the overall rotational structure. Without this balance, stars would either fail to form or burn themselves out far too quickly. This same negotiation plays out on larger scales. Galaxies survive for billions of years because rotation prevents them from collapsing into featureless blobs. Their stars orbit a common center, not because gravity demands it, but because angular momentum allows it. Remove that rotation, and the galaxy would contract violently. Increase it too much, and the galaxy would tear itself apart. Somewhere between those extremes lies stability. This balance becomes even more dramatic when gravity grows extreme. Near compact objects like neutron stars and black holes, rotation becomes the deciding factor between calm existence and catastrophic collapse. Matter falling toward these objects rarely plunges straight in. Instead, it forms accretion disks, spiraling inward while heating to extraordinary temperatures. In these environments, rotation does more than stabilize. It powers some of the most energetic phenomena in the universe. Jets erupt from the poles of spinning black holes, blasting matter and energy across intergalactic distances. These jets are not explosions. They are structured, columnated flows, guided by magnetic fields twisted and amplified by rotation. Without spins, such jets would not exist. What makes this unsettling is how often rotation acts as both a creator and a limiter. It allows structures to form, but it also sets boundaries on how compact those structures can become. There is only so much angular momentum that can be shed. Once that limit is reached, collapse stalls. This is why many systems end their lives not with a clean implosion, but with fragmentation, disks, rings, or violent ejections of material. Rotation forces matter to take detours. It introduces delay. It buys time. Even planets owe their survival to this tension. Earth does not fall into the sun because its sideways motion balances the inward pull. That sideways motion is inherited spin, translated into orbital momentum. Lose it, and the planet spirals inward. Gain too much, and it escapes entirely. Seen this way, orbit is not a path, it is a compromise. And compromises, once established, are remarkably durable. This durability explains why spin feels ancient. Once angular momentum enters a system, removing it requires work. It must be transferred elsewhere, radiated away, or redistributed. None of these processes are easy. Many take longer than the current age of the universe. As a result, rotation becomes a kind of memory, a record of past interactions, preserved not in shape, but in motion. This is why two otherwise similar objects can behave so differently. Two stars with the same mass may evolve along different paths because one spins faster. One may develop strong magnetic fields, another may shed material more violently. Spin subtly rewrites the rules of evolution, and yet rotation itself is not intelligent. It does not aim. It does not plan. It simply persists. This persistence forces the universe to work around it. Structures adapt. Energy flows reorganize. Stability emerges not from eliminating spin, but from accommodating it. Once you recognize this pattern, you start seeing it everywhere. Rings around planets, spiral arms in galaxies, flattened disks of gas around young stars. Even the rotation of Earth, giving rise to winds, currents, and climate patterns, is a small-scale echo of the same cosmic negotiation. Spin connects the very large to the very familiar. But there is still a deeper question waiting. If rotation shapes everything, if it stabilizes structures and powers extremes, why does it sometimes seem so unevenly distributed? Why do some objects spin rapidly while others barely turn? Why does angular momentum concentrate into narrow disks or thin jets instead of spreading evenly? Those questions hint at another layer of the story, one involving transfer, loss, and redistribution over time. Because while angular momentum cannot be destroyed, it can be moved. And how it moves determines what the universe becomes next. Rotation, once introduced, refuses to stay evenly spread. That turns out to be one of the universe's most important habits. Angular momentum doesn't like to sit quietly inside a collapsing system. It migrates, it leaks, it flows outward, even as matter falls inward. This creates a paradox that haunted early astrophysicists. If angular momentum must be conserved, how can stars ever form? A collapsing cloud should spin itself apart long before anything dense emerges. And yet stars exist everywhere. The resolution is subtle and deeply physical. Angular momentum is conserved globally, but it can be redistributed locally. Parts of a system can shed spin by passing it to other parts, much like dancers exchanging momentum on a crowded floor. One slows down so another can speed up. In collapsing gas clouds, this exchange happens through friction, turbulence, and shock. Gas does not fall smoothly. It collides, compresses, heats, and stirs. Each interaction allows small transfers of angular momentum, gradually pushing spin outward while mass moves inward. Over time, this produces separation. The inner regions become denser and slower, rotating. The outer regions absorb the excess spin and spread out. What begins as a chaotic rotating cloud organizes itself into structure. This is why disks form so naturally. A disk is not a design choice. It is the path of least resistance for rotating matter trying to collapse. But friction alone cannot explain everything. As telescopes improved, astronomers noticed something unsettling. Disks around young stars lose angular momentum far faster than simple friction could allow. Matter spirals inward efficiently, feeding the star, while spin is flung outward with suspicious effectiveness. Something else is at work. That something is magnetism. Gas in space is rarely neutral. It carries electric charge, even if only faintly. When charged particles move, they generate magnetic fields. When rotating gas clouds collapse, their weak magnetic fields twist, stretch, and amplify. These magnetic fields act like invisible threads tying different parts of the disk together. As inner regions rotate faster than outer ones, the field lines wind up, so creating tension. That tension transfers angular momentum outward, breaking the inner disk and accelerating the outer regions. This process is quiet, invisible, and relentless. It allows matter to fall inward without violating conservation laws. Angular momentum is not destroyed, it is exported. The result is growth. Stars gain mass, disks thin out. Planets begin to coalesce in calmer outer regions, where excess spin has accumulated. Without magnetic braking, star formation would be dramatically less efficient. The night sky would look emptier. This same mechanism scales upward. In galaxies, spiral arms act as angular momentum conveyors. Stars and gas interact gravitationally with these arms, exchanging energy and momentum. Some stars drift inward, others are flung outward. The galaxy slowly rearranges itself over billions of years, all while preserving its total spin. Rotation does not freeze structures in time, it reshapes them slowly. Even black holes participate in this dance. Matter falling toward a black hole forms an accretion disk because angular momentum cannot simply vanish. As material spirals inward, magnetic fields again twist and tighten, extracting rotational energy and launching jets at near light speed. These jets are not random outbursts, they are exhausts, channels through which excess angular momentum escapes. In a strange sense, black holes grow by getting rid of spin. What makes this unsettling is how universal the pattern is. From protoplanetary disks to quasars, from weather systems to galaxy clusters, rotation generates gradients. Those gradients drive flows. Those flows move angular momentum outward. Order emerges not by eliminating motion, but by organizing it. This also explains why rotation tends to concentrate into thin structures. A disk minimizes energy for a given amount of angular momentum. It is the most efficient configuration available. Any deviation increases internal stress, driving the system back toward flatness. Jets, meanwhile, are the universe's pressure valves. When angular momentum becomes too concentrated, it finds escape routes along axes where resistance is lowest. Narrow, focused, violent. None of this is designed. None of it is purposeful. It is simply what happens when rotating matter tries to change shape, and time plays a crucial role. These processes are slow, very slow. They operate over millions or billions of years. To human intuition, they feel static. But given enough time, they rewrite entire systems. This is why the universe appears calm yet dynamic. Why galaxies look stable even as they constantly rearrange themselves. Why stars shine steadily while quietly shedding spin through winds and radiation. Rotation is never resolved. It is only managed. And that management has consequences. Because angular momentum does not distribute evenly, some regions end up spinning much faster than others. Compact objects spin rapidly. Extended structures rotate gently. Extremes coexist. This unevenness is not a flaw. It is the reason complexity exists. If spin were perfectly uniform, structures would lack contrast. No disks, no jets, no differentiated systems. The universe would be smoother, quieter, and far less interesting. Instead, angular momentum concentrates differences, and those differences set the stage for something even more surprising. Because once rotation and gravity negotiate stability, another effect begins to matter. One that does not care about mass, magnetism, or collapse. It cares about direction. And that brings us to a deeper question. Why does spin have a preferred orientation at all? Why does the universe seem to remember which way is forward? That question takes us back, not to stars or galaxies, but to the earliest moments of the universe itself. At some point, tracing rotation backward stops being a problem of stars and galaxies and becomes a problem of origins. You can explain how spin moves, how it redistributes, how it concentrates into disks and jets, but eventually you arrive at an uncomfortable boundary. All of these explanations assume rotation already exists. They explain what happens after the universe starts turning, not why it ever started turning at all. This is where intuition breaks down, because the early universe does not resemble anything we are familiar with. There were no objects yet, no disks, no clouds, no reference points you could point to and say, this part is spinning faster than that part. The universe, at its beginning, was hot, dense, and astonishingly uniform. In every direction, it looked almost exactly the same, and yet the seeds of rotation were already there. The key is to understand that spin does not require solid objects. Rotation can exist as a statistical property of motion itself. Even in a nearly uniform universe, tiny variations in density and velocity are unavoidable. Quantum fluctuations ensure that perfect stillness is impossible. Motion exists everywhere, but not evenly. Some regions have slightly more momentum than others, slightly more directional bias, slightly more imbalance. At first, these differences are unimaginably small. They do not look like spinning systems. They look like noise. But gravity does something remarkable with noise. It amplifies it. Over time, Gravity pulls matter into slightly denser regions, and as those regions grow, they inherit whatever tiny angular momentum happened to be present. Conservation then takes over. What was once negligible becomes inescapable. This is how the universe remembers direction. As matter collapses, even the faintest initial twist gets magnified. A minuscule sideways drift in the early universe becomes a measurable rotation millions of years later. By the time galaxies begin to form, the question is no longer whether they will spin, but how fast and in which configuration. Crucially, this process does not require the universe itself to rotate as a whole. Observations strongly suggest that, on the largest scales, the universe has no preferred global axis. There is no cosmic spin like a giant wheel turning in space. Rotation emerges locally, not universally. It is born from imperfections, not from design. That distinction matters. If the entire universe were rotating, physics would look very different. There would be detectable anisotropies, preferred directions embedded in space-time itself. Instead, what we observe is subtler and more unsettling. The universe is globally neutral, but locally biased. Direction emerges without a director. This raises a deeper implication. Rotation is not imposed from above. It bubbles up from below. As the universe expands and cools, regions decouple from the cosmic flow. They stop expanding with space and begin collapsing under their own gravity. In doing so, they trap and preserve whatever angular momentum they carry. The expansion stretches space, but collapse sculpts motion. Over billions of years, this process repeats on every scale. Small regions collapse into stars. Larger regions collapse into galaxies. Entire clusters begin to rotate subtly around shared centers of mass. Each level inherits motion from the one before it, reshaped by local conditions but never erased. This is why spin feels so universal. It is not because everything was told to rotate. It is because nothing was allowed to be perfectly still. There is another layer to this story, one that feels almost philosophical. In physics, rotation is deeply tied to symmetry. A perfectly symmetrical system has no reason to favor one direction over another. But symmetry, in the real universe, is never absolute. It breaks. And when it breaks, direction appears. This is known as spontaneous symmetry breaking. The laws remain symmetrical, but the outcome is not. Think of a pencil balanced perfectly on its tip. The laws of physics do not prefer any direction for it to fall. Yet when it falls, it must choose one. That choice is not encoded in the laws. It emerges from tiny imperfections. The universe did something similar. Early on, conditions were nearly symmetric, but nearly is not enough. As expansion continued, slight imbalances were frozen in. Once frozen, they could not be undone. Gravity then took those imbalances and turned them into structure, motion, and eventually, rotation. Spin, in this sense, is the fossil record of broken symmetry. It tells us that the universe did not begin in perfect equilibrium. It began in a state that allowed choice, variation, and evolution. Rotation is one of the clearest signatures of that freedom, and this has consequences that reach far beyond astrophysics, because once rotation exists, it shapes time. Rotating frames behave differently from inertial ones. They introduce effects that cannot be transformed away. Even space-time itself responds. In extreme cases, such as rapidly spinning neutron stars or black holes, rotation drags space-time along with it, twisting the geometry of reality. The universe does not merely contain spinning objects. It reacts to spin. That reaction hints at something profound. Motion is not happening inside space-time alone. It is intertwined with space-time structure. Rotation leaves imprints not just on matter, but on causality, on clocks, on paths that light itself must follow. And this brings us to a final, unsettling realization. If rotation emerges from tiny asymmetries at the universe's beginning, and if those asymmetries were unavoidable, then spin is not an accident. It is a consequence of existence itself. A universe with structure cannot avoid turning, which leads to a question that feels less scientific and more existential. If everything spins because perfection was impossible, what else about the universe exists for the same reason? That question opens the door to the final stretch of our journey, where rotation stops being a mechanical property and starts revealing something about why the universe looks the way it does at all. Once rotation appears, the universe treats it as something precious, not in a poetic sense, but in a physical one. Spin is not easily erased. In fact, it is one of the hardest properties of motion to get rid of. You can slow objects down. You can dissipate energy as heat. You can radiate light away into space. But angular momentum behaves differently. It resists disappearance. It demands continuity. This is why rotation does not fade as the universe evolves. It sharpens. To see this clearly, forget galaxies for a moment and imagine something simpler. Picture a figure skater standing still on the ice, arms stretched wide. As they pull their arms inward, their rotation speeds up. Nothing external needs to act. No extra energy is added. The motion reorganizes itself. The same turning, compressed into a smaller radius, becomes faster and more intense. This is not a trick. It is not choreography. It is the universe enforcing a rule. Once spin exists, it must be accounted for. The same principle operates everywhere in the cosmos. When clouds of gas collapse to form stars, they begin large and diffuse. Any slight rotation they carry is almost imperceptible. But as gravity pulls the cloud inward, shrinking it dramatically, the rotation accelerates. What was once barely detectable becomes dominant. The cloud flattens into a disk, not because it chooses to, but because rotation leaves it no alternative. This flattening is not cosmetic, it is structural. Rotation fights collapse along one axis while allowing it along another. The result is order carved out of chaos. Disks, rings, or spirals, these are not aesthetic accidents. They are rotation made visible. This is why stars form with disks around them, why planets orbit in roughly the same plane, why moons follow similar paths. Rotation organizes systems long before intelligence ever notices them. And once the system settles, the spin remains locked in. This persistence has a strange side effect. Rotation creates memory. A spinning system carries information about its past. The direction, speed, and orientation of rotation encode the conditions under which the system formed. Long after the original chaos is gone, the spin remains as a fossil. Galaxies remember the motions of the early universe. Stars remember the collapse of ancient clouds. Planets remember the turbulence of their birth disks. Even atoms carry intrinsic spin, a quantum echo of symmetry and structure at the smallest scales. Nothing forgets how it started turning. What makes this unsettling is how universal the rule is. Rotation is conserved not because it is useful, but because the universe cannot violate it without breaking deeper symmetries. Space itself enforces this conservation. There is no preferred orientation in empty space. No direction that physics favors. Because of that, any rotation that exists cannot simply dissolve into nothing. There is nowhere for it to go. This is a subtle point, but it matters deeply. Energy can disappear locally because it can spread out. Heat radiates away, light escapes, motion becomes randomness. But angular momentum is directional. It requires a frame. To remove it, something else must take it. And in the vast emptiness of space, there is often nothing available to receive it. So rotation accumulates. As systems interact, they exchange spin. Collisions redistribute it. Mergers amplify it. Over cosmic time, angular momentum flows from small scales to large ones, shaping structures far beyond their origins. Galaxies gain spin not just from their own collapse, but from interactions with neighbors, from tidal forces, from the gravitational pull of surrounding matter. This is why large-scale structures rotate, even when no single component appears responsible. The universe behaves less like a collection of isolated objects and more like a network through which motion circulates. And yet, despite all this exchange, the total rotation never vanishes. It merely changes hands. This leads to an important realization. Rotation is not just motion through space. It is motion about space. It encodes relationships. It tells you how parts of the universe are connected, how they influence one another, how they evolve together rather than alone. Which brings us to something counterintuitive. Rotation creates stability. At first glance, spin seems destabilizing. It flings matter outward. It resists collapse. But in reality, rotation allows systems to exist at all. Without it, gravity would pull everything straight inward. Stars would collapse more violently. Galaxies would lack structure. Planetary systems would never settle into long-lived configurations. Spin provides balance. It introduces tension between collapse and escape. That tension creates time. A star lives for billions of years because rotation and pressure counteract gravity. A galaxy persists because spin prevents it from collapsing into a featureless lump. Even black holes, the ultimate sinks of matter, retain spin as one of their defining properties, shaping the space around them in ways that light itself must obey. Rotation does not oppose gravity. It negotiates with it. And this negotiation has consequences for how the universe evolves. Systems with higher angular momentum behave differently from those with less. They form different structures. They cool differently. They distribute matter in distinct ways. Over time, rotation becomes a sorting mechanism, separating possible futures. Two regions starting with nearly identical conditions can diverge radically based on slight differences in spin. One becomes a disk galaxy, another becomes an elliptical cloud of stars. One forms planets, another does not. Rotation is not destiny, but it biases destiny. This idea extends even further. At the deepest level, spin is tied to the identity of particles themselves. In quantum mechanics, spin is not literal rotation, but it behaves like angular momentum. It determines how particles interact, how they stack, how matter becomes solid rather than collapsing into a featureless state. Without spin, chemistry would not work. Atoms would not form stable shells. The periodic table would not exist in any recognizable way. The world you experience is shaped by rotational rules, operating at scales far below perception. So when we say everything spins, we are not describing a surface-level phenomenon. We are describing a structural principle. Motion prefers continuity. Direction resists erasure. The universe does not like stillness, which raises a question that lingers beneath all of this. If rotation is conserved so stubbornly, if it accumulates and organizes and stabilizes, then what happens at the limits? What happens when rotation becomes extreme? When spin is no longer a gentle organizer, but a dominating force? That question leads us towards some of the most exotic objects ever discovered. Places where rotation bends space-time itself and challenges our intuition about cause and effect, and the flow of time. And that is where we're headed next. When rotation intensifies beyond a certain threshold, it stops behaving like a background feature and starts asserting itself as a force that reshapes reality. At everyday scales, spin feels passive. A spinning wheel turns, but the room around it remains unchanged. A rotating planet moves through space, but space itself seems unaffected. That intuition works only because the rotations you experience are small, slow, and weak compared to the structure they inhabit. At cosmic scales, that assumption breaks down. As mass increases and rotation accelerates, the distinction between motion and geometry begins to blur. The universe does not merely contain spinning objects. Under the right conditions, spin reaches outward and alters the fabric that holds everything together. Space stops being a neutral stage. It becomes responsive. This is not metaphor, it is literal. Einstein's theory of general relativity revealed something unsettling. Mass tells space how to curve, and motion tells space how to twist. A rotating object does not just move through space-time. It drags it along. The faster and denser the rotation, the stronger the drag. Imagine stirring thick honey with a spoon. The honey near the spoon moves easily, but farther away the motion fades. Space behaves similarly, except the thickness is not resistance, but geometry itself. Near a rapidly spinning mass, space is compelled to rotate along with it. Farther away, the effect weakens, but it never fully vanishes. This phenomenon is known as frame dragging, but the name understates how profound it is. Frames of reference made the invisible scaffolding that defines motion, rest, and direction are no longer fixed. They are carried by spin. In such regions, standing still becomes impossible. Near an extreme rotating object, you could not remain motionless even if you tried. Space itself would move beneath you. Your definition of not rotating would lose meaning. The universe would force you into participation. This is where rotation stops being optional. The clearest expression of this effect appears around spinning black holes. These objects are not merely dense, they are rotationally saturated. When a massive star collapses, it does not shed its angular momentum. The rotation it carried as a star becomes compressed into a much smaller volume. The result is a black hole spinning at a significant fraction of the maximum allowed by physics. Around such an object, space behaves in ways that defy everyday reasoning. There exists a region where no observer can remain stationary. Even light paths are twisted. Time itself flows differently depending on how you move, relative to the spin. This is not science fiction. It is the consequence of rotation interacting with gravity at its most extreme. Yet what makes this especially striking is that nothing fundamentally new is happening. No exotic force is introduced. No special exception is made. The same conservation of angular momentum that made ice skaters spin faster now sculpts the geometry of the universe. The rule simply refuses to weaken. This continuity is what makes the universe feel coherent across scales. The same logic governs spinning tops, hurricanes, planets, stars, galaxies, and black holes. Rotation is not layered on top of physics, it is embedded within it. But here, the narrative takes an even stranger turn. Rotation does not only shape objects, it shapes causality. In rotating space-time, the paths that events can follow are altered. The future is no longer aligned the same way for all observers. Cause and effect remain intact, but the routes between them curve and twist. Signals take unexpected paths. Horizons form not just around mass, but around motion. This means rotation introduces boundaries that do not exist otherwise. In extreme cases, there are regions where space flows faster than light would travel through empty space. Not because anything locally exceeds the speed of light, but because space itself is moving. The distinction matters, and it unsettles intuition in exactly the way the universe seems to enjoy. Here, rotation reveals its deepest role. It is not just about things turning, it is about how the universe allows change to propagate. Without rotation, space-time would be simpler, flatter, and more predictable, but it would also be less capable of structure. Spin creates gradients. It introduces asymmetry. It provides handles that gravity can pull on and shape. This interplay explains why rotating systems are often the most dynamic, luminous, and energetic objects in the universe. Accretion disks blaze with radiation, jets launch at near light speeds, magnetic fields twist and reconnect. All of it traces back to the conservation and concentration of spin. Energy alone does not produce this complexity. Direction matters. And yet, despite all this drama, rotation remains strangely invisible. You do not feel Earth's spin. You do not sense the galaxy's rotation carrying you around its center. Even the cosmic expansion happens without resistance or sensation. The universe is moving constantly, but it does so in a way that preserves local calm. This is why rotation feels paradoxical. It dominates structure while hiding from perception. That concealment has consequences. For centuries, humans assumed the heavens were static or perfect. Motion belonged to Earth. The stars were eternal and fixed. Even when planetary motion was accepted, rotation remained subtle, secondary, almost decorative. Only when observation sharpened did the truth emerge. Nothing was still. The universe was not a quiet backdrop. It was a choreography. And that choreography began early. Rotation was not added later. It emerged naturally from the universe's initial conditions. Tiny irregularities grew. Collapses amplified motion. Interactions transferred angular momentum across scales. What started as minute imbalances became defining features. The universe did not choose to spin. It had no alternative. This realization reframes how we think about beginnings. Creation was not a pristine explosion followed by motion. Motion was woven into creation from the start. Spin is not a consequence of the universe existing. It is part of what existence means in a universe with space, time, and symmetry, which leads to a deeper question, one that cannot be ignored much longer. If rotation is so fundamental, if it shapes matter, space, time, and causality, then what started it in the first place? Was there an initial spin? Or did rotation emerge inevitably from something even more basic? That question pulls us backward toward the earliest moments we can meaningfully discuss, and toward the limits of what explanation itself can offer. And that is where we go next. Rotation feels like something that must be caused. In everyday life, things spin because something pushes them. A hand twists a knob, a motor turns a wheel. Cause storm begins when winds shear and collide. Motion seems to require an instigator, a before and an after, a still state disturbed into movement. That intuition follows us backward when we ask where cosmic rotation began. It is tempting to imagine the early universe as perfectly smooth and motionless, exploding outward uniformly, only later breaking into spinning pieces. That picture is emotionally satisfying. It preserves the idea that order came first and complexity followed. But it is also deeply misleading. The early universe was never perfectly still. Even in its earliest describable moments, the universe was not a silent, symmetrical expansion. It was uneven, slightly lopsided, imperfect in ways that mattered enormously. Those imperfections were not flaws. They were the seeds of everything that followed. To understand why rotation was inevitable, you have to abandon the idea of absolute symmetry. A universe that is perfectly uniform has nowhere to go. Nothing distinguishes one direction from another. No gradients exist. No preferred motion can arise. Such a universe would be sterile. Our universe was not. Tiny variations in density, unimaginably small differences in energy distribution, existed almost immediately. Where matter was slightly denser, gravity pulled a little harder. Where it was slightly thinner, expansion won. These differences were subtle, but gravity is patient. Over time, it amplifies the smallest imbalances. As matter began to fall inward toward these denser regions, something unavoidable happened. Perfectly straight collapse is nearly impossible. For matter to fall inward without rotation, every particle would need to move directly toward the center, along perfectly radial paths. Any sideways deviation, no matter how small, introduces angular momentum. And once angular momentum exists, it cannot simply disappear. This is the crucial point. The early universe did not need a grand twist or a cosmic shove to start spinning. It only needed imperfection, a slight misalignment. Their tiny sideways motion. From there, physics did the rest. As collapsing regions shrank, their rotation sped up. Conservation of angular momentum ensured it, just as a figure skater spins faster when pulling in their arms. Collapsing clouds of gas spun more rapidly as they contracted. The universe did not choose rotation. It inherited it. This inheritance is relentless. Every time matter collapses under gravity, rotation intensifies. Clouds become disks. Disks fragment into stars. Stars form planets. Planets retain spin. Systems within systems preserve and redistribute angular momentum, but they never erase it. This is why flat structures are so common in the cosmos. Accretion disks around stars, spiral galaxies, rings, planets orbiting in roughly the same plane. Rotation does not just survive collapse, it organizes it. Spin acts like a sorting mechanism. Motion perpendicular to the rotation plane gets damped through collisions and interactions. Motion aligned with rotation persists. Over time, chaos flattens into structure, not because chaos disappears, but because rotation selects which motions endure. This explains why the universe looks the way it does, but it also raises an unsettling implication. If rotation arises inevitably from imperfection, then a universe with time and gravity can never be fully still. Motion is baked in, even if expansion were perfectly uniform, which it wasn't. Quantum fluctuations alone would introduce asymmetry. At the smallest scales, absolute stillness is not even definable. Rest is an approximation. This realization reframes the question of beginnings. Asking what started rotation may be the wrong framing entirely. Rotation may not have begun as an event. It may be a consequence of existence unfolding under rules that forbid perfect symmetry. The universe does not tolerate balance for long. This is why spin appears everywhere, even where no obvious cause remains. Galaxies rotate even in regions with little interaction. Particles possess intrinsic angular momentum without spatial extent. Black holes spin, not because they were wound up, but because collapse preserved motion that could not be eliminated. The deeper you look, the less rotation feels like an add-on. It feels like a bookkeeping rule the universe refuses to violate. And that rule connects the smallest scales to the largest. The same mathematics that governs spinning electrons echoes in the rotation of galaxies. The same conservation laws apply without regard for size, time, or context. This unity is unsettling because it removes the comfort of explanation by scale. There is no special layer where rotation originates and then trickles down. It exists everywhere simultaneously, enforced by the structure of physical law itself. Which leads to a quiet but profound realization. If rotation cannot be erased, only transferred or transformed, then motion never truly ends. Systems slow down locally, but their angular momentum leaks outward. Stars lose spin to planets. Planets lose spin to tides. Galaxies redistribute rotation through mergers. The universe constantly rearranges motion, but it never deletes it. This makes rotation a kind of memory. The universe remembers its past through spin. Every rotating system carries information about the asymmetries that shaped it. Even billions of years later, that information has not been fully erased, and that raises a new tension. If angular momentum is so stubborn, so fundamental, then what happens at the ultimate limits? What happens when systems merge completely, when collapse reaches its endpoint? When nothing remains to redistribute motion, that question pulls us toward the most extreme objects known, and toward the realization that rotation may place hard limits on what the universe can and cannot become. And that is where the story turns next. As systems grow larger and denser, rotation stops being a subtle background effect and becomes a dominant constraint. It does not merely decorate structures, it resists them. At enough scale and speed, spin becomes a force that actively prevents matter from doing what gravity would otherwise demand. This is easiest to see when things collide. When two clouds of gas merge, their combined angular momentum does not cancel neatly. Even if they approach from opposite directions, tiny asymmetries remain. Those remnants add. The result is not stillness, but rotation amplified. The merged system spins faster than either cloud alone, not because energy was added, but because angular momentum had nowhere else to go. This principle governs everything from star formation to galaxy mergers. When galaxies collide, they do not simply collapse inward into a dense ball. Instead, they stretch, twist, and sling material outward. Long tidal tails form. Disks warp. Stars are flung into elongated orbits. Rotation prevents clean collapse. It injects messiness into gravity's desire for simplicity. The universe is not allowed to compress freely. This becomes even more dramatic at smaller, denser scales. Consider a collapsing star. Gravity pulls inward relentlessly, squeezing matter toward the center. If gravity were the only actor, collapse would continue smoothly until nothing recognizable remained. But rotation changes the script. As the star shrinks, its rotation speeds up. Centrifugal effects grow stronger. At some point, inward collapse is no longer symmetrical. Material near the equator resists falling straight in. It spreads outward, forming disks or rings. Angular momentum reshapes the collapse itself. This is not a secondary detail. It is decisive. Many stars do not become black holes or neutron stars simply because their rotation prevents it. Spin can hold matter up against gravity long enough for other processes, radiation, nuclear reactions, mass loss, to intervene. Rotation buys time. Sometimes it saves the system entirely. Even when collapse succeeds, spin leaves a permanent mark. Black holes are not defined only by mass. They are defined by mass and angular momentum. A spinning black hole is fundamentally different from a non-spinning one. Its event horizon behaves differently. Space itself is dragged around it. Paths that would otherwise be straight become twisted. This phenomenon, known as frame dragging, is not metaphorical. Space and time near a rotating mass are literally pulled along with the spin. The universe does not merely contain rotation, it responds to it. This is where intuition truly fails. We tend to imagine rotation as motion through space. But at extreme scales, rotation reshapes space itself. The geometry bends, the rules of cause and effect stretch. Even the definition of still becomes ambiguous. Near a rapidly spinning black hole, nothing can remain stationary. Not because it is moving, but because space itself is moving. The universe has created a region where rest no longer exists as a meaningful concept. This reveals something essential. Rotation is not just something objects do. It is something space-time accommodates, and that accommodation comes with limits. There is a maximum rate at which an object can spin. Beyond that, stability breaks down. Material tears away. Orbits destabilize. Even black holes have a theoretical spin limit. Exceeded, and the equations stop making sense. The universe enforces boundaries. This suggests that rotation is not an infinite resource. It cannot grow unchecked. When angular momentum becomes too concentrated, it must be redistributed. Matter is expelled. Energy is radiated. Systems shed spin in dramatic ways. Jets erupt from accretion disks. Stars fling material outward. Galaxies eject gas into intergalactic space. These are not accidents. They are pressure valves. Spin builds up, and the universe vents. This process is deeply counterintuitive because it inverts our expectations. We think of explosions as energetic events driven by heat or force. But many of the universe's most violent outflows are driven by rotation trying to rid itself of excess angular momentum. The faster something spins, the harder it is to hold together. This is why disks are thin, why rings form, why structures flatten instead of clumping. Rotation prefers extension over compression. It spreads matter outward along planes rather than letting it fall inward isotropically. The result is a universe shaped by compromise. Gravity pulls inward, rotation pushes outward. The structures we see are the negotiated outcome between these opposing tendencies. Nothing wins completely, and this negotiation never ends. Even long after a system appears stable, angular momentum continues to migrate. Planets slow their rotation through tidal interactions. Moons drift outward. Stars spin down over billions of years. Galaxies exchange angular momentum with their surroundings. Spin leaks. This leakage is subtle but cumulative. Over cosmic time, it reshapes systems without dramatic events, quietly, persistently, always obeying the same conservation laws. Which leads to a deeper, more unsettling realization. If angular momentum must be conserved globally, then the universe as a whole carries an accounting of all the spin it has ever generated. Nothing has been lost. It has only been rearranged across scales and epochs. This raises a question that feels almost philosophical, but is grounded in physics. Does the universe itself rotate? At first glance, the answer appears to be no. On the largest scales, the universe looks isotropic. There is no preferred axis, no global spin has been detected. But absence of evidence is not proof of absence. And more importantly, the question itself may be poorly posed. Rotation requires an external frame of reference, something to rotate relative to. For the universe as a whole, there is no outside, no background grid, no fixed axis. This does not mean the universe is non-rotating. It means the concept may not apply cleanly. Instead, what we observe is local rotation everywhere, emerging naturally from initial asymmetries and preserved relentlessly through cosmic evolution. The universe does not spin like a wheel. It fragments into countless spinning systems, each obeying the same rule: spin without a spinner. This reframes the role of rotation yet again. It is not a global property imposed from above. It is an emergent inevitability arising wherever matter interacts, collapses, and evolves under time and gravity. Which brings us to a quiet but powerful conclusion in waiting. Rotation is not something the universe added later. It is not a feature layered on top of expansion, structure, or time. It is a consequence of imperfection playing out under conservation laws that allow no exceptions. And that means the universe never had the option to remain still. What remains to explore is not whether everything spins, that is now unavoidable, but why spin appears even where matter barely exists, and what that says about motion at the deepest possible level. That is where the story turns next. At this point, rotation stops looking like a byproduct of structure and starts resembling a baseline condition, something that appears even when there is barely anything there to rotate. This is where the intuition built from planets and galaxies finally collapses. Because spin does not begin with stars. It begins far earlier, at scales where there are no clouds, no disks, no collisions in the familiar sense. Long before gravity gathers matter into shapes, rotation already exists, embedded in particles themselves, in ways that do not map cleanly onto anything you can visualize. An electron does not spin like a tiny sphere. It has no surface to turn, no axis you could point to, no circumference tracing a circle, and yet it possesses angular momentum. A measurable, quantized form of spin that behaves exactly like rotation in every experiment that matters. This is not metaphor. It is not a naming convenience. It is a property that responds to magnetic fields, that conserves angular momentum, that couples to other spins and aligns, anti-aligns, and transfers influence just like rotating objects do. But nothing is rotating. This is the first place where the word spin begins to mislead. At the quantum level, spin is not motion through space. It is something deeper, a structural feature of how particles exist. And yet, it obeys the same conservation laws that govern planets and galaxies. Angular momentum does not care about scale. This continuity is unsettling because it suggests that rotation is not something added to matter when it becomes large. It is something matter carries from the beginning, regardless of size or composition. Even empty space is not exempt. Quantum fields, the scaffolding beneath particles, possess fluctuations that carry angular momentum. These fluctuations appear even in vacuum, even at absolute zero. Space is never perfectly still. It vibrates, it twists, it exhibits structure that cannot be eliminated. Rotation exists without objects. This forces a re-evaluation of cause. If spin appears in particles that were never pushed, never collided, never assembled from rotating components, then rotation is not always inherited. Sometimes it is fundamental. The universe does not merely allow spin, it produces it. To understand why, you have to abandon the idea that motion requires intent or force. Instead, motion emerges from symmetry, and more importantly, from the breaking of symmetry. In physics, perfect symmetry is fragile. The slightest imbalance amplifies over time. When conditions change rapidly, as they did in the early universe, symmetries fracture. Fields settle into states that are not perfectly uniform. Directions appear where none were specified. Spin is one of those directions. In the earliest moments after the universe began expanding, energy fields cooled and differentiated. Forces separated, properties crystallized. In that transition, tiny asymmetries froze into place. Angular momentum was among them. Once created, it could never disappear. This is the same rule you saw at larger scales, now applied universally. Angular momentum, once present, must be conserved. It can be redistributed. It can be hidden in internal degrees of freedom, but it cannot be erased. So the universe inherited spin at birth, not as a global rotation, but as a scattered endowment distributed across particles, fields, and future structures. This inheritance propagates upward. Particles form atoms, atomic spins couple. Atoms form molecules, molecular rotations define chemistry. Chemistry builds dust grains. Dust grains collide, align, and spin. Clouds inherit that motion. Stars inherit it from clouds. Planets inherit it from stars. Nothing starts from zero. At no stage does the universe reset the ledger. This is why attempts to imagine a perfectly non-rotating system always fail in practice. Even if you could eliminate visible motion, microscopic angular momentum remains. Thermal agitation reintroduces it. Quantum uncertainty guarantees it. Stillness is not a stable state. This realization reframes rotation yet again. It is not simply a response to gravity or collision. It is a statistical inevitability in any system with degrees of freedom and time to evolve. Time matters here. Spin requires duration. It is a relationship between change and persistence. Without time, rotation has no meaning. And the universe has had a great deal of time, enough for even the smallest asymmetries to become significant, which leads to an uncomfortable conclusion. The longer the universe exists, the more rotation it accumulates in structured ways. Not because angular momentum increases, but because it becomes organized, coherent, visible. Early spin was chaotic, random, scattered. Over billions of years, gravity and interaction sorted it, aligned it, amplified it at larger scales. Rotation is order emerging from noise. This is why galaxies exhibit coherent spin directions internally, even though the universe has no preferred direction overall. Local order does not imply global bias. It implies evolution under conservation laws, and those laws are ruthless. They do not care about aesthetics. They do not optimize for simplicity. They enforce accounting. Every bit of angular momentum must be somewhere, carried by something at all times. When you view the universe through that lens, rotation stops being mysterious and starts being unavoidable. Any system that evolves, interacts, and persists will spin in some form. The deeper mystery shifts. If spin is so fundamental, why does it take the forms it does? Why discrete values at the quantum level? Why specific distributions at cosmic scales? Why certain alignments and not others? These are not philosophical questions. They are empirical ones, and they point toward a deeper structure governing how motion and symmetry intertwine, which brings the story to its most subtle turning point. If rotation is everywhere, conserved, and fundamental, then it is not merely a feature of the universe. It is a constraint on what the universe is allowed to become. Certain configurations are impossible, not because they violate energy limits, but because they cannot accommodate angular momentum. Entire classes of hypothetical universes collapse under that requirement. Spin is not decoration. It is a gatekeeper. And that means the universe we observe is not just one of many possible arrangements. It is one of the few that satisfy the quiet, relentless demand that something must always be turning. What remains is to confront what this implies for beginnings, endings, and the ultimate fate of motion itself. Because if spin cannot vanish, then the universe may never truly come to rest. That question is where the final arc begins. Once you accept that spin cannot be destroyed, the idea of a quiet ending becomes difficult to defend. Most popular visions of the universe's future are built around stillness, heat death, maximum entropy, a long fade into darkness where nothing interesting happens anymore. Stars burn out, galaxies drift apart, energy spreads thin until no gradients remain. It sounds calm, but calm is not the same as motionless. Even in the most diluted future imaginable, angular momentum remains. It has nowhere to go. And as structures dissolve, that rotation does not vanish, it fragments. This is where intuition fails again. When galaxies stop forming stars and their disks lose definition, it feels like rotation should slow, then stop. But what actually happens is redistribution. Spin migrates from larger coherent structures into smaller, harder to track reservoirs. Black holes are one of them. As matter spirals inward, it transfers angular momentum outward, spinning the hole faster. Over cosmic time, black holes become some of the most rapidly rotating objects ever formed. They are not static sinks. They are engines of stored motion. And when black holes eventually evaporate through Hawking radiation, an unimaginably slow process, even that angular momentum must be released back into the universe, particle by particle, photon by photon. Nothing is allowed to keep it forever. Even radiation carries spin. Photons possess angular momentum. Gravitational waves do too. Motion does not require mass. It only requires structure and time. So the far future is not still. It is diffuse. Rotation does not disappear. It becomes subtle. At that stage, the universe resembles a sea of weak, overlapping motions, tiny spins embedded in particles that rarely interact. No large structures remain to showcase rotation dramatically, but the underlying accounting remains intact. This reframes entropy. Entropy is often described as disorder increasing, but disorder does not mean inactivity. It means energy and motion spread out so evenly that no work can be extracted. Everything still moves. It just moves without purpose. Spin contributes to that picture. It becomes noise instead of signal. This is why a truly motionless universe is not just unlikely, it is incompatible with the laws that governed its birth. Angular momentum conservation ties the past to the future. Whatever rotation existed early on must echo forward indefinitely. Even cosmic expansion does not erase it. As space stretches, distances grow, interactions weaken, and structures dissolve. But expansion does not absorb spin. It only dilutes the way spin can express itself, which raises a deeper question. If rotation is so fundamental, is it telling you something about time itself? Spin is directional. It distinguishes clockwise from counterclockwise. It encodes orientation. And orientation requires a sequence, a before and after. In other words, rotation presupposes time. Some physicists suspect the relationship runs both ways, that the arrow of time and the persistence of spin are linked, that conservation laws do more than preserve quantities, they stabilize causality. If angular momentum could vanish, certain sequences of events could unravel. Symmetries would break in catastrophic ways. Predictability would collapse. Spin is part of what keeps the universe intelligible. This is why attempts to imagine physics without conservation laws tend to fail. Without them, nothing holds. No structure persists long enough to matter. Rotation, then, is not just movement, it is memory. Every spinning object remembers its past interactions. Every conserved quantity is a record of what happened before. The universe carries its history forward through these constraints. You are looking at a system that never forgets. This realization loops back to the beginning in a subtle way. You started with a simple observation. Planets spin, stars spin, galaxies spin. It seemed like a coincidence. Pay pattern waiting for explanation. What emerges instead is something far more restrictive, a universe that cannot choose otherwise, a universe where motion is not optional, where stillness is unstable, where rotation is woven into existence from the smallest scales to the largest futures, which makes the original question feel inverted. It is no longer, why does everything spin? It is, how could anything ever not spin? That inversion matters, because it shifts the burden of explanation. Rotation does not need a special cause. Non-rotation would, and that means the universe you inhabit is not animated by accidents piling up over time. It is shaped by rules that quietly enforce continuity, direction, and motion, whether you notice them or not. The remaining task is to bring this understanding back to human scale, not to glorify it, not to romanticize it, but to recognize what it says about your place inside a system that never truly stops moving. That final turn is where the conclusion will land. Long before anyone could calculate angular momentum, long before equations existed to describe it, humans already lived inside rotation without realizing it. You are sitting on a planet that spins at roughly 1,000 miles per hour at the equator. You are also being carried around the sun at tens of thousands of miles per hour. And on top of that, the entire solar system is orbiting the center of the Milky Way at a speed that dwarfs both of those motions combined. Yet none of this feels like movement. Your body does not sway. Your vision does not blur. There is no wind screaming past your face. The floor beneath you feels solid, stable, fixed. Evolution trained your senses to detect sudden changes in motion, not constant ones. A steady spin is invisible to a nervous system designed for survival, not cosmic awareness. This is the first human trap. For most of history, motion was something you experienced directly. Walking, running, falling, being thrown. Movement meant effort. Spin, when noticed at all, appeared only in obvious cases. A thrown stone, a spinning wheel, the stars wheeling overhead at night. Early civilizations noticed that the sky turned. They did not think the earth was spinning. They thought the heavens were. The stars became a vast rotating shell, a cosmic ceiling that revolved reliably every night. It was a reasonable conclusion. From the ground, that is exactly what it looks like. The idea that the Earth itself might be rotating was deeply unsettling. If the ground was spinning, why weren't objects flung off? Why didn't birds struggle to keep up? Why didn't clouds lag behind? Those objections weren't foolish. They were based on everyday experience. Rotation, as humans understood it, always came with forces you could feel. The missing piece was inertia. If everything shares the same motion, no internal signal reveals it. A smooth rotation carries you along quietly, like being inside a sealed train moving at constant speed. Without windows, without bumps, motion disappears. This realization took centuries to solidify. When it finally did, it shattered not just astronomy, but intuition itself. The Earth was no longer a passive stage beneath the cosmos. It was an active participant, spinning relentlessly, indifferent to whether its inhabitants noticed. Once that mental barrier fell, everything else followed. If Earth spins, why not the sun? If the sun spins, why not the stars? If stars spin, why not entire galaxies? Each step widened the scale but reused the same logic. Rotation was not an exception. It was the default, and still, the human mind resisted. Even today, people struggle to internalize this. Diagrams help, animations help, numbers help, but the lived experience remains stubbornly static. You feel still, so stillness feels real. This disconnect matters because it shapes how people imagine the universe. A static intuition leads to flawed expectations. It encourages the idea that motion needs explanation, while rest does not. Physics says the opposite. Motion persists unless something intervenes. This is why rotation appears everywhere once you start looking for it. Any asymmetry, any imbalance, any slight offset in forces during formation gets locked in. Conservation does the rest. When gas clouds collapsed into stars, tiny differences became permanent spins. When stars collapsed into remnants, rotation intensified. When galaxies assembled, angular momentum dictated their shapes long before gravity finished sculpting them. None of this required intention. None of it required design. It required only time and the refusal of the universe to forget motion. This is where the human story becomes humbling. You are not standing on solid ground. You are riding a layered system of rotations nested inside one another, like gears too large to visualize. Your daily stillness is borrowed stability, not fundamental rest. And yet this does not make life chaotic. In fact, rotation creates reliability. The day-night cycle exists because Earth spins. Seasons emerge because that spin is tilted. Climate patterns, weather systems, even biological rhythms are anchored to rotational regularity. Spin is not noise. It is structure. The same principle scales upward. Galactic rotation stabilizes star orbits. Planetary rotation shapes atmospheres. Stellar rotation influences magnetic fields. Everywhere motion is constrained, patterns form. The universe does not spin wildly at random. It spins in ways that last. That endurance is what allowed complexity to emerge at all. And that realization quietly sets the stage for the next step in the story. Because if rotation stabilizes systems, then extreme rotation must push them toward failure. There is a limit, and discovering where that limit lies is where things begin to break in genuinely surprising ways. Rotation feels gentle when it's slow, almost polite. A planet turns, a galaxy drifts. Nothing seems strained. But rotation carries a hidden tension that only appears when speed increases beyond what matter can comfortably hold together. Every spinning object lives in a negotiation. On one side, gravity and internal cohesion pull inward, trying to keep everything bound. On the other, rotation creates an outward tendency, not a force in itself, but a consequence of motion that resists being pulled toward the center. The faster something spins, the louder that resistance becomes. For most objects in the universe, this balance settles quietly. Earth spins fast, but not fast enough to tear itself apart. Its gravity comfortably wins. The same is true for the sun, for planets, for most stars. Rotation shapes them, flattens them slightly, stirs their interiors, but does not dominate them. But the universe does not stop at most. Somewhere along the scale of size and density, rotation begins to push back hard enough to matter. Imagine spinning a wet towel. Slowly, it just twists, faster, and droplets begin to fly outward. Spin faster still, and the towel itself strains, fibers pulling tight as the motion tries to rip it apart. Celestial objects behave the same way, just without fibers and water. As stars form, rotation speeds up naturally. Gas clouds collapse under gravity, shrinking in size. Conservation of angular momentum ensures that as they get smaller, they spin faster. This is not optional. It is unavoidable. Most of the time, excess angular momentum is shed. Material is flung outward into disks. Jets form. Systems stabilize. But sometimes, the collapse outruns the escape. This is where things become extreme. Neutron stars are born from stellar death, and they carry rotation to an almost absurd degree. When a massive star collapses, Its core shrinks from something the size of a city to something closer to a mountain. Whatever rotation it had before becomes compressed into that tiny volume. The result is an object that can spin dozens, hundreds, even thousands of times per second. At that speed, rotation is no longer a subtle influence. It defines everything. A rapidly spinning neutron star flattens dramatically. Its magnetic fields twist into tight coils. Radiation beams sweep through space like cosmic lighthouse signals. Matter at the surface experiences forces that no solid could survive under Earth conditions. This is spin pushed to the edge of physics, and even here, the universe enforces a boundary. Spin cannot increase forever. There is a breakup point, a speed at which outward motion overcomes gravity and cohesion completely. Beyond this threshold, matter is no longer bound, it escapes. For planets, this limit is far away. For stars, it is closer. For compact objects, it is terrifyingly near. Black holes take this to its logical conclusion. A rotating black hole represents angular momentum trapped so completely that it reshapes space-time itself. The spin does not sit on the black hole. It drags the surrounding universe with it. Space twists, time tilts, orbits behave in ways that defy everyday logic, yet even black holes have a maximum spin. There is a hard limit written into relativity. If a black hole spins too fast, the equations break. The event horizon destabilizes. The object cannot exist in that configuration. Nature does not allow it. This is one of the most important clues in the entire story. Rotation is universal, but it is not infinite. It grows, intensifies, concentrates, and then it stops. Everywhere you look, angular momentum piles up until something gives. Matter rearranges. Energy radiates away. Systems find new configurations that obey the same ancient rule. Motion is conserved, but structure must survive. This tension explains why the universe looks the way it does, why galaxies are disks instead of spheres, why stars flatten at the equator, why planetary rings form, why accretion disks glow, why jets shoot outward instead of inward. Spin organizes chaos, but it also limits it. For humans, this boundary is difficult to grasp because it operates far beyond direct experience. Nothing in daily life spins fast enough to threaten its own existence. We live comfortably below the danger zone, but the universe spends a surprising amount of time right on the edge. Every collapsing system flirts with rotational failure. Every newborn star sheds spin to survive. Every galaxy balances angular momentum against gravity across billions of years. Rotation is not a decorative feature layered on top of physics. It is one of the constraints that shapes what can exist at all. And this brings the story to a deeper question. If spin is everywhere, and if it cannot grow without limit, then something must decide how much rotation systems start with in the first place. That question does not live inside stars or galaxies. It lives at the beginning. Because the most unsettling possibility is this: the universe may not have acquired rotation later. It may have been born with it. And if that's true, then spin is not just a property of things inside the universe. It may be a property of the universe itself. That idea leads to consequences far stranger than any rotating star, and it's where the story goes next. If everything spins, the natural instinct is to look backward. Backward past stars, past galaxies, past the first atoms, past even space as we know it. toward the earliest moments when the universe was smaller, hotter, and simpler than anything that exists today. At first glance, that early universe should have been perfectly calm. The standard picture describes it as hot, dense, and expanding uniformly in all directions. No preferred direction, no up or down, no left or right, just smooth outward growth like an inflating balloon. And in a perfectly symmetric expansion, there should be no overall spin. This expectation matters. In physics, symmetry is powerful. When a system begins perfectly balanced, nothing inside it should spontaneously choose a direction without a reason. Rotation requires a symmetry, a bias, however small, that breaks perfect uniformity. So here's the problem. The universe today is not neutral. Galaxies rotate, clusters rotate. Large-scale flows of matter show coherent motion across immense distances. Angular momentum is not localized. It is everywhere. If the universe began in a state with zero net rotation, then every bit of spin we observe must have emerged later, from tiny irregularities amplified over time. That sounds reasonable, until you examine how much spin actually exists. When astronomers measure the angular momentum of galaxies, they find values far larger than simple models predict. The numbers don't just suggest rotation, they demand it. Something injected motion early, efficiently, and universally. This raises an uncomfortable possibility. What if the early universe was not perfectly symmetric? Even an unimaginably small deviation, a slight imbalance in density, velocity, or expansion rate, would be enough. Once expansion begins, conservation laws do the rest. Tiny twists become permanent. Small biases grow as structures form. The universe does not forget motion. It preserves it. During the earliest phases after the Big Bang, matter and energy were coupled tightly. Regions were not isolated. Interactions stretched across what would later become enormous distances. Any initial asymmetry would have been shared, distributed, and locked in before expansion diluted direct contact. This is not speculation pulled from thin air. It's the same principle that governs every spinning system we understand. You see it when a collapsing gas cloud spins up. You see it when a skater pulls in their arms. You see it when a star contracts and its rotation accelerates. The difference is scale. In the early universe, the object collapsing or expanding was everything. That makes the question subtle. We are not asking whether the universe spins like a wheel. We are asking whether motion had a directional memory from the start, whether expansion carried a faint rotational imprint that no later process could erase. Most cosmological models assume no global rotation because it simplifies the equations. A non-spinning universe is mathematically clean, predictable, elegant, but nature is not obligated to prefer elegance. Observations hint at alignments that shouldn't exist if everything were perfectly random. Some large-scale structures appear correlated in orientation. Certain patterns in the cosmic microwave background resist complete explanation by noise alone. None of this proves a rotating universe, but it keeps the door open. More importantly, it reframes rotation as something inherited, not generated. Instead of asking, why did galaxies start spinning? The better question becomes, why didn't they start still? If motion is conserved absolutely, then stillness is fragile. Any slight departure from perfect balance persists forever. Expansion does not erase rotation, it preserves it. This idea explains why rotation appears universal without requiring a universal spin axis. You don't need the cosmos to rotate as a whole. You only need the early universe to be imperfect, and imperfections are inevitable. Quantum fluctuations ensure that no state is ever perfectly uniform. At the smallest scales, uncertainty is not a bug, it's a feature. Even the smoothest early universe would have contained tiny variations in energy and motion. Those variations became the seeds of everything. Density differences became galaxies. Temperature differences became structure. Velocity differences became angular momentum. Spin, in this sense, is not something added later. It is something revealed. As matter clumped under gravity, angular momentum that had always been present suddenly became visible. Collapsing regions amplified it. Disks formed. Orbits emerged. Rotation became obvious only once systems condensed enough to show it. This reframing changes how you see the universe. The spinning galaxy is not a product of chaos. It is a fossil, a record of motion that predates stars, planets, even atoms. A memory from an era when the universe was young enough that everything touched everything else. And once you see spin this way, another realization follows. Rotation is not competing with expansion. It coexists with it. The universe expands outward, while local systems spin within that expansion. These motions do not cancel. They layer. Expansion sets the stage. Rotation sculpts the details. That layered motion explains why the cosmos looks dynamic rather than frozen. It is not just growing larger, it is internally restless. But this still leaves one question unresolved. If spin is inherited, conserved, and amplified, why does it organize into such clean, structured forms instead of dissolving into randomness? Why don't galaxies tumble chaotically? Why do disks form instead of clouds? Why do orbits settle instead of collapsing into noise? The answer lies not in where rotation comes from, but in how it interacts with gravity over time. And that interaction is where the universe reveals one of its most counterintuitive habits. Motion doesn't just survive and it self-organizes. That's where we go next. If rotation were just leftover noise, the universe would look very different. Matter would fall inward without restraint. Clouds would collapse straight down, piling into dense knots with no preferred shape. Stars would form abruptly and violently. Planets, if they formed at all, would plunge directly into their stars or scatter into space without stable paths. But that is not what you see. Instead, the universe is filled with disks, thin, elegant, rotating disks. Galaxies flatten, star systems spread outward. Rings appear wherever gravity and motion negotiate instead of collide. This is not an accident. It is the inevitable outcome of rotation interacting with gravity over time. Gravity pulls inward. Rotation resists collapse sideways. Neither wins completely. The result is balance, not stillness, but structure. When a cloud of matter begins to collapse under gravity, any tiny amount of rotation becomes decisive. As the cloud shrinks, that rotation speeds up. Conservation demands it. What was once negligible becomes dominant. Inward motion accelerates spin. Spin redirects collapse. Instead of falling straight down, matter spreads into a plane. Energy dissipates through collisions, but angular momentum does not vanish, it reorganizes. This is why disks form. Disks are not special structures imposed by physics. They are the most efficient compromise between gravity and rotation. They allow matter to fall inward while preserving motion. They allow systems to settle without destroying themselves. The same principle applies everywhere. A galaxy is a rotating disk because it formed from collapsing matter with angular momentum. A solar system is a flattened plane because its parent cloud could not shed rotation completely. Even planets spin because the material that built them carried motion long before they were solid. Rotation is not decoration, it is architecture. Once a system acquires angular momentum, that momentum becomes a stabilizing force. It prevents runaway collapse. It creates predictable paths. It allows time to pass without catastrophe. Orbits exist because straight-line collapse is forbidden by conserved motion. This is why rotation is so deeply linked to habitability. A non-rotating Earth would not just lack day and night, it would lack long-term stability. Climate, magnetic fields, and even geological processes depend on rotation interacting with internal dynamics. At larger scales, the same logic applies. Galaxies that rotate slowly tend to be chaotic. Their stars move on random paths. Their shapes are irregular. In contrast, galaxies with well-defined rotations show order, longevity, and resilience. Rotation gives systems memory. It allows them to remember their past while evolving forward. And this brings the story full circle. The reason everything spins is not because the universe chose rotation. It is because once motion exists, physics refuses to erase it. Instead, gravity reshapes it, time amplifies it, structure locks it in. Spin is the universe's way of keeping track of itself. Every rotating object carries a record of earlier motion. Every orbit encodes a history of collapse and resistance. Every disk is a negotiation frozen into form. Even at the smallest scales, angular momentum behaves the same way. Particles possess intrinsic spin, not because they rotate like tiny balls, but because the laws governing them demand quantized motion. The concept of rotation survives even where classical pictures fail. From quantum fields to galaxy clusters, the rule is consistent. Motion persists, organizes, and constrains what is possible. A universe without spin would be simpler, but it would also be sterile. No long-lived structures, no stable systems, no gradual evolution, just collapse, dispersion, and erasure. The universe you inhabit is not static because it cannot be. It is dynamic because motion is conserved, amplified, and sculpted into form. And once you see that, spinning stops feeling mysterious. It becomes inevitable. Which brings us to the final realization. Spin did not begin as a feature. It began as a consequence of imperfection, conservation, and time unfolding in one direction. Everything spins because nothing was ever perfectly still. And the universe has been remembering that ever since. At the beginning, spinning felt like a detail. A planet rotates, a galaxy turns, a particle carries something we call spin, separate facts, separate scales, nothing that seemed to point toward a single rule. But now that picture has shifted. Spin is not something the universe decorates objects with. It is something the universe refuses to erase. Once motion exists, even faintly, even imperfectly, it becomes permanent. Expansion stretches it across space. Gravity concentrates it into structure. Time carries it forward without ever letting it disappear. The spinning Earth beneath your feet is not rotating because it was wound up like a toy. It spins because motion existed before Earth did, before the sun did, before atoms themselves had names. The galaxy overhead turns not by coincidence, but by inheritance, preserving momentum older than its stars, older than its light. Even stillness turns out to be an illusion. There is no true rest, only motion layered on motion, organized just enough to last. What feels stable survives because rotation allows it to. What endures does so by remembering how it once moved. And maybe that's the quietest truth hiding in all this. The universe doesn't pause. It doesn't reset. It carries its past forward, not as memory, but as motion. If this kind of calm exploration resonates with you, you can like the video, subscribe to the channel, and leave a comment telling where you're watching from and what time it is there. Those small signals help this space reach other curious minds, one at a time. For now, though, let the motion fade back into the background. The universe is still turning, and so are you.